Okay, time for another key idea or key concept video to do with the topic of vectors. So we should all be familiar with the idea that a vector is a quantity with both magnitude and direction. And so we tend to depict vectors using arrows like this. And the key concept I want to get across is that when we describe vectors, we describe them in terms of their constituent parts. So we're used to seeing that in the context of I and j vectors. So you have something like this, that the vector A can be described in terms of an x component along an I direction. So if I mark on a set of axes here, an x component along this I direction, and I is the unit vector along this I direction, and a y component along a j direction like that. And what I want to get across is that we're constantly in the business of determining the amount of a vector which acts in a specific direction. And the way that I described this in the lecture this morning was to talk about this I and j here as being like the ingredients that we are mixing together, and this ax and ay as being the quantities of those ingredients. So any two vectors in this two-dimensional plane will have the same ingredients. They'll both be composed of a certain amount of I and a certain amount of j, but the quantities of those ingredients is what determines the kind of character of our vector, if you like. And the key thing that I went through in the lecture was the idea of a dot product. So we have the definition of a dot product as being the magnitude of the vector A times the magnitude of the vector B multiplied by the angle in between those two vectors. So in this context, we have two vectors like this with some angle in between them. And what I was trying to get across in the lecture was how the dot product basically tells us the alignment between these two vectors. So if the vectors are perfectly aligned, then this angle goes to 0, and we would have the situation where A and B are both acting in this direction. Cosine theta would be 0. And what that essentially means is that these vectors are perfectly aligned. And so the dot product is just the magnitude of these two things multiplied together. In the case that they are perfectly misaligned, so I have A acting in one direction and B acting in the other, and there's a right angle in between them, and they're orthogonal to each other, then this cosine theta, well, cosine of 90 degrees is 0, and then the dot product becomes 0. Okay? So the dot product is basically a measure of how well aligned two vectors are. And this actually is related to this idea of expressing a vector in terms of its components. Because if I take the dot product between a vector A and one of these directions, so let's first of all write out our definition of our vector again. So we have a certain quantity of our vector which acts in this I direction and a certain quantity of our vector which acts in this j direction. What I pointed out in the lecture is if I take the dot product between A and some unit vector I, well, that tells us how much of the vector acts in this I direction. And to prove that, we can just substitute in our expression for our vector here, so axi plus ayj. If I take the dot product with I, which is what we just expanded out A here, well, now I need to worry about what the dot product between this vector I and this vector I is and what the dot product between j and I is. So if I take the dot product between I and itself, well, the definition of the dot product is just the magnitude of the two vectors multiplied by the angle in between them. Well, this is the same vector. So that the angle is obviously 0. So we get cosine of 0, so this is just equal to 1. And the magnitude of I, well, I is a unit vector, so these are both 1 as well. So this is actually just equal to 1. If I take the dot product here, so I'm going to get the dot product between j and I. So I get j dot I. Well, that's equal to the magnitude of j times the magnitude of I. Well, that's just going to be 1 again. But this time the angle is different. The angle in between j and I, remember, we've drawn it out on the previous slide. So we have j here and I here. And so there's 90 degrees in between them. So cosine theta in this case is cosine of 90 degrees, and that's just equal to 0. So the dot product between j and I is 0. And putting all of that in, so this is just our kind of working out, putting all of that in, we get that a dot I is just equal to ax, because this term becomes 1 and this term becomes 0. So what we're showing here is that if I take the dot product with a unit vector in a given direction, it tells us how much of our vector is pointed in that direction. And this becomes incredibly important for determining components of forces and so on. So this is when we come to resolving forces or resolving vectors, this is actually the process we're going to go through. And of course, you will still use the kind of trigonometric interpretation of this, where we have a sort of right angled triangle, and I have here my x component and here my y component, and this is my vector A. And I can compute the lengths of the sides of this triangle using trigonometry and simply say that AX is equal to the magnitude of A cosine theta and AY is equal to the magnitude of A sine theta. But it all comes from this definition, and that's really important for us. So just remember this idea that taking the dot product between two vectors tells us essentially the alignment between those two vectors. And in the case where one of those vectors is a unit vector, what it tells us is how much of A is acting along that direction.